structures that we have. What happened? Okay. So this is the example of the microstrip that we have here. This is just a photo. Okay, we can have just a single element. As you can see that this is a single element. Okay, the single element is just one structure here, as you can see. Okay, so we also have Yagi Uda. So this is what you call the weapon. Cannot charge. Okay, so you can see that if you have only one structure, so that is called the single element of microstrip. Okay, at the first photo that you can see here. And then also sometimes you have like beside one single element, you have Yagi-Uda type of antenna, where in this case, as you can see, that the microstrip antenna consists of the feeding as well as the ground plane and some directors here. So if you have this thing, this is called the Yagi-Uda types of microstrip antenna. And then we also have in terms of the array. If you have more than one element, you call that is the array elements. So this is another important. You see. So we have in terms of this array element. So it depends on what is the applications that you want to do. And also we have different array types. Like you can have a series with the coplanar array series, and also we have like this one. You can see that here. So this is what we call the secular. So this is another type of array antenna here. So you can see that this is another match antenna, like let's say array as well. So this is a series feed with a corporate. So this is with a corporate series feed as well. So this is just a planar microstrip antenna because you have the direction of Y and X here. Okay, so you have both Y and X. So this is called planar. If you only have one like this, okay, so you can see that this is a linear. We also can have the structure like this. Okay, you arrange in terms of a secular. So this is in terms of the secular here. Okay, so this is just an example of the same. But the important thing here, this is the single elements here. Single elements mean you only have one element in your particular. You can see that here. So this is the example of microcenter. Please remember the difference between the planar antenna and microstrip antenna, because don't ever try to confuse. Planar antenna, actually microstrip is part of the planar antenna actually. Okay, planar antenna, there is a lot of division. You just can have a dipole antenna, you can have only slotted antenna, you can use a transmit array, that kind of thing, using the FSS and so on. So that is called the planar antenna. Microstrip antenna is part of the planar antenna, where the structure, the ground plane is under the substrate itself. So under the substrate, so you have the ground plane. I can show it to you later. So this is an example of the microstrip antenna. As you can see, as I mentioned to you, microstrip antenna is a metallic strip or patch mounted on a dielectric layer, which is supported by a ground plane. As you can see that, okay, from this rectangular microstrip antenna, as you can see that you have a ground plane, you have a substrate, you have the patch element. Okay, so what you can see that here, the most important thing of this particular structure, as you can see from the microstrip, is your length. Length is actually half wavelength. Usually is half wavelength. L is usually half wavelength. Okay, half wavelength means the resonance that the frequency can be occurred. So it's much depend on what is the length of your patch itself. The patch, as usual, you can see that you have the patch, and then there is the edge. The radiating edge. The radiating edge coming from the edge of your antenna itself. Okay, so you can see that if you have your L here, so you can see that there is some electromagnetic fields going in and out. Okay, from your this. So from the patch itself. So as you can see here, if you have the substrate here, so you can have the substrate. This is your antenna, this is a substrate. So the patch will be like this, the patch will be like this, the patch will be like this, triangular and so on. So this is all this, and then there is the ground plane here. Okay, this is the ground plane. Okay, so this is a patch. So this is the ground plane. As you can see that the radiating come from here. This is the most important. So this is so where the radiating, and you can see that it goes from this L. L is actually is the resonance frequency. Yeah. So this is what we call the half wavelength of your antenna itself. Okay. So of course you have a substrate. The substrate that you use, sometimes you use FR4, sometimes you use Rogers, Taconic, and so on. So that is the substrate. Or if you want to use the what we call the textile, so that means you need to characterize first. If you want to use a textile, you need to characterize this parameter first before you can put it into your simulation. Because if you don't know this particular value of your epsilon r, it's difficult for you to design this particular length and W of your patches. So this is a very, very simple. But if you buy the FR4 Rogers or Taconic, usually they give you already in terms of the structure itself, or what we can say that in terms of the parameters, they will give you in terms of your epsilon r, they will give you in terms of thickness, the H there, they give you in terms of your tangent delta, loss tangent, so that basically if you know all this value, you put into the simulation. From the simulation, they will give you all the results, the gain, efficiency, directivity, and etc. Okay, so this is very important for you to understand about this. Yes, is there anybody want to talk? If you don't understand, just let me know. Okay, so this is a, okay, so you can see that we have a patches of various shapes here. You have in terms of square, we also can have the rectangular, just a dipole, circular, elliptical, triangular, ring ends, etc. Even though you can put your names as well, your name to become the resonating elements as well. Okay, we did also in terms of the, we did the logo of U3M as a resonator. You can find it from my publications as well. And then we made in terms of the different patches, size, etc. So again, the most important thing here, what we can see that the best shape that we still can have is just the rectangular or the circular. So that is the optimum shapes that we, because the other shapes difficult to determine in terms of the resonance here because of the structures. But the most important thing, the resonance is come from the length of the structure itself. Okay, of course, in terms of the antenna itself, we can have in terms of the advantages and disadvantages. Of course, the first of all, the microscope antenna is a low profile, okay, conformable to non-planar surface, of course, simple and expensive, medically robust, compatible with MMIC, monolithic micro-integrated circuits, very versatile into our resonant frequency, polarization, phase impedance. So what we can see at the what we call the resonant, the microswitch antenna also can have a different polarization. You can increase the bandwidth, you can increase, you can have a pattern, you can have the impedance difference, so on. Disadvantages, of course, you say low power, because they cannot handle high power like microwave waveguide, narrow bandwidth. Okay, this is another disadvantage. So that's why the people is trying to find out how to improve the bandwidth of the microstrip. Usually the bandwidth of microstrip or 2 or 3, 1 or 2 to 3% only. So it's very difficult to get wider bandwidth. So that's why when I evaluate some of the, they say, oh, they have a very good microstrip bandwidth because we have a very high bandwidth for microstrip. That one actually is actually most of them is doing that is not a microstrip, so it's a planar types of antenna. Okay, so you for the microstrip you cannot get bandwidth more than 3%, 3%, because that is on. So that's why we need to find a method. So that's why they try to increase the substrate thickness. You know, we try to make in terms of the epsilon r value higher, lower, and etc. to have the. But if you want to know more details about how to improve the bandwidth, maybe you can refer from some other books on the microstrip antenna. They focus on technique to improve the bandwidth of this antenna. And then of course we have large EM signature at certain frequency outside the operating band. Okay, in large array, trinovity bandwidth and scan volume. And of course, last okay, of course, if you go for the low frequency as usual, if you go for the low frequency, the structure will become big because of the resonance is half wavelength. Okay, as you know that low frequency, lambda is bigger, half of the lambda, so you can imagine. So that's why for the microstrip, it's not suitable to be used at VHF band because of the structure itself. Okay, right. So as you can see that here, this is feeding. So of course, if you create or if you design this kind of microstrip antenna, so you need to fit where is the positions that the antenna is matched toward your transmission line. Okay, so as you can see that we have different feeding techniques. Okay, like you can use in the microstrip feed line, the first one. Okay, so where you need to draw the line. I think if you take the microengineering, you know already how to draw the microstrip line. So you just make sure that your microstrip line is matched toward your antenna itself. For example, if you want to match it with the 50 ohm, you try to find the positions that where is the 50 ohm occur in your line. Because throughout the length itself from this antenna, as you can see that the variations of your impedance throughout this particular resonant frequency. We will see it later. And then you also can use in terms of coaxial. Coaxial means you fit underneath of the antenna itself. So you need that. You need to find the position as well. But usually the position for the microstrip line and coaxial feed line is almost very identical, very similar. The only things that you need to push a bit for the microstrip feed line like this one so that you can feed it directly. But for the coaxial feed line, as you can see that you just take your your coaxial cable, you just put it okay underneath of that so you can have this. Then we also can feed using aperture couple feed, so you need to have some aperture here and as well as proximity here. So you can see that this is aperture here, and then this is the difference between this is underneath you need to have like this the aperture could be any size like this, and then you need to have. But this one, you have in terms of proximity, you make this transmission line is underneath the substrate, and this of course your ground plane here. Okay, so you put, that means you need to have a 2 layers, same thing as this aperture as well. This one is a single layer, so this one also is a single layer. Okay, so this is, and of course, if you talk about the microstrip, they're easy to fabricate, so you can just use based on your PCB techniques before. Simple to match by controlling the inside feed, position, and then low spurious radiations. And of course, we know that the microstrip feed has a very narrow bandwidth. And then as the substrate height increases, the surface with proliferation. So this is disadvantage in terms of the microstrip. If you increase the substrate thickness, actually you are producing more surface width. So what we can see that spurious radiation will be increases as well. Okay, so this is an example of the microstrip line feed here. So this one we try to find out in terms of the feed where we try to adjust this position, okay, to have a 50 ohm. So we try to, and then this one we use in terms of gap coupling here. Okay, so this is gap coupling. So we also can feed at the center with this gap coupling. And this is the models that they do in terms of this particular antenna. And then this is the model. So for the for this one, this is a step, as you can see that. So it composed of this inductance and capacitor. For the gap, we always have only the capacitance here. Okay, so also we also can use a microstrip line feed here in this case. So this is what you call the inset feed. Okay, most of the time I'm using the inset feed, where you need to find out, okay, let's say for example Z0 here. Z0 here is a 50 ohm here. So you need to find the position that where is a 50 ohm. So this is the 50 ohm here. All right, so and then for this one, we try to adjust this to make it the 50 ohm as well. Okay, for this one, what we see, this is we make the microslide at the radiating edge here. So radiating edge is mean that you have this Okay, so this is your radiating edge come from. And then of course, for this one, the radiating edge is like this as well. But you can fit at the radiating edge. This one we fit at the non-radiating edge. This one we fit at the radiating edge. This one we fit at the radiating edge as well, but different position. We also can fit this antenna at the non-radiating edge here. So here is a non-radiating edge. So you can have whether you want to, so yeah, you can see that this is a radiating edge. So as you can see that this is L, where if you have an L, so the radiating edge is coming from there, right? So the first one, the picture shows that you are matched towards the radiating edge. The second diagram is a non-radiating edge. So the non-radiating edge, we want to find the position of this. Okay, so this one is a 50 ohm. So you just move here. So from this value, so you can see that this is a 50 ohm. So this is just the techniques where you can fit your antenna to be matched, in this case. Okay, so if you model this, as you can see that, okay, so this is the inside field radiating edge, and then this is the non-radiating edge here. Okay, right. So if you look detail about this coaxial fit, of course, coaxial fit is easy to fabricate and match. And then we have very look at that you fit underneath here. So as you can see that, so it's easy to fabricate, low spurious radiation. Of course, simple to match by controlling the position. And then the thing as usual, we can have a very narrow bandwidth and more difficult to model for thick substrate. So this is part of it. Okay, so this is the example of the coaxial probes where you have the antenna on the top of there, and then you have a ground plane, and then you match toward your coaxial cable here. Okay, for the aperture couple fits, this is easier to model. Why we say that? Because of you need to find out in terms of the modeling techniques. And then moderate spurious radiation, ground plane between substrate isolate to fit. Okay, so another thing, as you can see, the rating element minimize the interference, independent and optimization of the fit rating element. So it means that in this aperture coupled fit, we do not disturb in terms of the radiations elements. And then most difficult to fabricate, of course, you need to have more adjustment, low bandwidth as well. Typically, high altimeter is used for bottom substrate and thick and low side constant for the top, fit line with lot size and position electrical. Okay, so these are examples of the aperture couple. You can see that there is a couple here, the what color, the purple here, and the brown here is your transmission line. So you couple the energy to the aperture there, the small aperture. The aperture, it depends. Sometimes we just use in terms of rectangular, sometimes you can use in terms of circular, triangular, and so on. So it's different, different aperture techniques that you can use in order for you to match with this particular antenna. Okay, in terms of the proximity couple feed, we also have the largest bandwidth. So you can see that if you use this technique, you can have about 13%, quite high, the bandwidth for this antenna. And then easier to model, low spurious radiation, more difficult to fabricate, and length of feeding to stop and width to line ratio of patch can control match. Okay, so this is an example of your proximity feed. So where you can define this as a capacitor between the line, and RLNC is the resonance for this particular antenna that is there. Okay, so what you can see here, meta-analysis models, as you can see that we have a transmission line model, cavity model. So this is the different models that I just showed. So, but we are focusing on this transmission line model only. The rest, if you want to know more detail, so you can write, or you can, read from the books on the microstrip. Okay, for the why we use the transmission line model, because it is very simple, has a physical insight, and another thing, of course, this model is a bit less accurate. Cavity model more complex, more accurate, and has physical insight. or integration model, equation models. Of course, it's very complex, very accurate, very versatile, and less physical inside. Okay, so most of the simulation software, they are using this kind of integrals, all this kind of equation. So this is about the microstrip. As you can see there, I think you learned in your microwave engineering before, transmission line model. So you can model your transmission line, okay, for the microstrip line. As you know that the microstrip line consists of the line where you need to design based. So the thing, the width. The width will determine what is the impedance of your line. Okay, so what you need to do, of course, you need to have your epsilon r, you need to have your h, and t is the thickness of your copper. Usually that one's not really, it's okay. And then you also can have in terms of electric field lines here. But what we can see here in terms of epsilon r for the microstrip, they are talking about the epsilon r effective. Remember, because of why they use into epsilon r effective, because of you have the epsilon r, the dielectric constants of the material, and also you have the dielectric constant of the air. Okay, so remember that you have the air as well. So that's why in order for you to calculate all this value, you need to take the consideration of your epsilon effective. Okay, so that's why most of the antenna, most of microstrip transmission and microstrip, so they are using the value of your epsilon r effective. So this is the example of E and H fields for the microstrip case. And then you can see in terms of the field, okay, from microstrip in terms of the W is the width of the line, H is the thickness. So this is just a picture to show how the field inside your microstrip. So of course, as you can see that you have in terms of E and H, you have the E usually is the perpendicular to H for the TEM. But for the microstrip, as you learned before, this is in terms of the quasi-TEM. Okay, so how you will get this value? So you can refer from Kai Chang. So you need to find W over H. Okay, so from there you can find the Z naught. Okay, for the narrow strip, I think this one I just put it here to make sure that you know this how to calculate the value of your microstrip. Okay, so this is synthesis. So for white strip, when Z naught is left, this value, so you can use this equation. And alternative Z naught is known at first, so you can find your epsilon effective. So microstrip lines on aluminum, as far as that, this actually appear to be accurate to plus minus 0.2 over the impedance range of 8 less than Z naught less than 45 ohm. Okay, so because I put it here, I have one on the Kai Chang, another one is on the POSA. So this one I took it from the POSA book. So this is the effective, the standard effective that the concern on microstrip line that almost the people is talking about. Epsilon E is equal to this, and this is the characteristics impedance. From this particular value, you can find the Z naught. But the most important thing here, you need to find the epsilon effective first. And then from this epsilon effective, you put into the equation so you can find the of your Z naught. So you have to make sure that you can find what is W over D. D, as usual, from the substrate itself, we know D or H is the same. Okay, W is the width of that, and then you can calculate what is your Z naught here. Okay, so this is just a synthesis, how we want to get W over D using this synthesis from the POSA books. Okay, so that is about the microstrip. I just briefly explained to you how do you get all that value for the microstrip. Okay, so as you can see there from the pad itself, so we have two slots here. One is slot 1, as you can see from the picture, and we also have a slot 2 here. So this is the field coming from the patch to the ground plane here. So we model based on values of your inductance with the subsectance here. Conductance with the conductance, where the slot 2 represented by G plus JB and another one also G plus J. Each radiating aperture is modeled as a narrow slot of width W and height H radiating into a half space. Okay, right. So what you can see here, so as usual, you can see that this is the transmission line model. So as you can see that this is a transmission line model. Okay, so what we have, this is a slot 1, this is a slot 2 here. So you model it. So maybe this one is one, slot one, this is slot two here. Okay, so the model based on G plus JB. Okay, so this is the resonance, your L here. Okay, so what what we can see here, this is a back, horizontal and vertical of E, and then this is a fringing field, fringing field from this. So what you have here, so you can excite here. So you excite your field, okay, towards from ground plane to your inductor here. So because the field will be moving from your from the patch to the ground plane, or from the ground plane to the patch here. Okay, what we can see here in terms of this characterization of rectangular magnetic. Okay, so this is the L again. I show you here L. So this is your field inside the substrate, and then this is a fringing field. Habis malah. Dia tak charge lah sekarang saya punya ni. Saya tak sure sebab. Dia tak charge, susah, tak apalah. Okay, so as you can see that here, we can see into our radiating slot. Radiating slot is given as this one. So as you can see, because of the L will produce into all the fringing field. So that's why you have your delta L here. Okay, and then as you can see that this is a current distribution and voltage throughout this patch. As you can see that you have a voltage, okay, and the current here. So the current is what we have here is the current minimum at the edge there, and then you can have a maximum, okay, from here. So you can see that this is how the model. Okay, so fundamental TM10 mode or rectangular microscope antenna. If is the situation, then the A1, B is a voltage, and dot 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 is a current variations, and C is a two radiating slots, and D is equivalent transition line model. Okay, so what we can see that this is a okay. So how we get the slot value here? So you can find the slot number one here actually is equal to Y1 equal to G1 plus JB. So as you can see that we model the slot is G1 plus JB1, where your G1 is represented by this. You can refer from the Balanis book, and B1 is represented. W is the width of the patch. Lambda naught is your operating frequency. Okay, K naught is actually is 2 pi over lambda. H is your dielectric substrate thickness. Okay, and then the B1 is equal to this. So you can use this when you have H over W naught is less than 1 over 10. Okay, similarly for slot number 2, okay, so it means that you can have in terms of slot 1 and slot 2, we assume that it's the same equations that you use. Okay, right. If V naught is the voltage across center of the slot, we can define a conductance such that when placed across the center of the slot, will dissipate the same power as rated by the slot. Thus, what we can see that G is equal to 2P over this. And then if you have all these equations, okay, so you can see that G is equal to this value, I1 over 120 pi square, I1 is equal to. So what we have here, we have this particular value here. Okay, so G here. So G here, G is actually, you can find the R later on. G actually is equal to 1 over R. R is to determine your resistance, your impedance. So we can use in terms of when W is to less than lambda naught, you can also use this one. When W is equal to lambda naught greater than W naught, you can use that one. W is the width of the patch, lambda naught is the operating frequency. This one, lambda naught is based on there is no dielectric. So that means that you are using the just the velocity of light. Okay, so If you don't know what is lambda naught actually is the VC equal to F lambda. So you can have, so usually you know this operating frequency, so you know this, so you can find the lambda naught. Okay, right. Okay, so this is the conductance value when you talk about slot width, W. So they give you in terms of the graph that maybe you can get it from here. Okay, the most important thing here is we want to find what the input impedance of this particular patch antenna. The slight reduction from lambda d over 2 is necessary to account for the fringing at the radiating edges. If the reduction of L from lambda d over 2 is properly chosen, properly the length reduction factor Q, the transfer meters of the slot number 2 become this lah, G1 minus JB1. In order for the patch to have a broadside pattern, it's desired to excite the slot 180 degree out of phase. So this is accomplished by choosing the length slightly less than this particular value. So the length, or sometimes we use the lambda G here, they put a lambda D is equal to lambda naught over square root of your epsilon R. Okay, so the slot 1, you have G1 plus JB1, and G2, you have G1 minus JB1. So as you can see that your Z in here actually is equal to 1 over 2 G1. G1 is the conductance of the antenna itself. So if you can find, so this is the simplest equations that we use in order. But sometimes you want to know more detailed equations, you need to use what we call the mutual couplings between these two slots. Okay, so this is a mutual coupling. So you can see that taking into account coupling, so you need to have this one, a G12. Okay, this one is more complicated, the equations that you use. So it depends on you. Okay, so usually we need to use in terms of program to program the G12 value, where positive is used with odd antisymmetric resonant voltage and negative is used with even symmetric resonant voltage distribution between the patch and the between the slot. Okay, so this is the on G2, how we want to get the value of your G2 here. So you can see that G12 is equal to this particular long equation with some Bessel function here. All right. How you want to determine the effective dielectrics? So what I think the values for the effective dielectric is very similar with the microstrip as well. So you can find based on this, when you have W over H is greater than 1, so you can use this equation to determine the effective dielectric constant. And this is just a graph to show that different frequency with the dielectric constant versus your log frequency here. Okay, so you have a different value of your substrate. Okay, F substrate is 2.33, 6.8, and 10.2, and then they make it in terms of the graph to make sure that you easy for you to to do this. Okay, so for the microstrip as well, what you can see here, we have this as you know that this is the fringing field. This is your L here. Okay, fringing field here. So for the fringing field, sometimes you need to model with the value of your delta L here. Okay, so your delta L actually is equal to this equation. All the equation will be given in your exam. No need for you to remember. If you can remember, that's much better. And then you can see that this is a frequency, so you can have in terms of this. Okay, so how you want to determine in terms of length here? L effective actually is to L plus 2 delta F. So what we can see here, okay, the effective length. So if you want to find what is the L actually is your your L effective, you minus with your fringing field both. So you have in terms of this. If sometimes if you use this, you can have more accurate value compared to the second one. So the resonant frequency with no fading is given by this. Because of the fringing, the effective distance rating edges seems longer than L by amount of delta L edge. So to be slightly less than F naught by factor Q. So Q is just a filling factor that you can use it in your equation as well. Okay, so this is the filling factor. Factor Q has been determined using the model expansions here. Okay, so this is what we can see. The fringing effect increases with the increased substrate thickness. This leads to larger effective distance between the edges and approximately linear decreases. Okay, so next, I want, since we have only another 10 minutes, so I can show you how to design this antenna next week. So how you want to design the microstrip patch antenna here? First of all, you need to specify the substrate that you're using, the resonant frequency, and what is the H over lambda knots that you want to find. Of course, you have to determine the value of your W, L. From this determine W, so you can, so that means here, the W can be determined for efficient radiator, a practical which leads to good efficiency is equal to. So what we have here actually is the same thing as half wave length as well. W is equal to V naught over 2F, square root of your 2 over epsilon R plus 1. So they take consideration this one as the epsilon R plus 1 divided by 2 here. Okay, so they take some sort and not the average value between epsilon R, because this is epsilon R A here. Okay, so it's equal to 1. So just the divide by 2. So this is the plot of W as a function of frequency as shown in the attached figure. So this is the example of this is what we call the element W versus the frequency here. As you can see that, okay, the frequency. So if you want to find epsilon R is 2.2, 2.2 is here. For example, this is a 2.2 value. So let's say we want to have 1 here. So this is your W. Okay. So this is what how they do in terms of value. But you can just use a calculation based on this value. And once you know the W, of course, you can find the L. L, you know, from this equation, V naught epsilon effective unit consideration minus 2 delta L. Delta L is the fringing fields that I chose. So from here, you determine already the value of WN. Okay, so actually microstrip is not really difficult to design. Okay, for the rectangular, you need to find the W and L. So if you know what is the L here, what is you know is the W here. So you know what is the resonance here. So it means that the patch of this antenna is much depend on the operating frequency. If your operating frequency is higher, you can find that your patch antenna is getting smaller. So that's why if you design a millimeter wave, sometimes it's only maybe about, sometimes it's very small, like 3 millimeter only. So any change on this value will change the resonant frequency. So it is very sensitive. So that's why if you design a 2.4 or you design 3.5, it's okay for the microstrip. So it's not really hard. But if you design a millimeter wave, example 30 gigahertz or maybe 100 gigahertz, you can find out your antenna here. It's very, very small. Sometimes it's difficult in terms of the length to determine, because any change of the length will change the frequency. Even though 0.01 millimeter also